Welcome to our exploration of one of the most important experiments in physics history, the cathode ray experiment. The cathode ray experiment, conducted by J. Thomson in 1897, revolutionized our understanding of atomic structure and led to the discovery of the electron. This groundbreaking experiment not only discovered the electron but also showed that atoms are not indivisible as previously thought. Let's examine the cathode ray tube apparatus that made this discovery possible. The tube contains two metal electrodes, a negative cathode and a positive anode, sealed in a glass tube with most air removed. When high voltage is applied, mysterious rays travel from the cathode toward the anode, creating a glowing spot on the fluorescent screen. The fluorescent screen at the end glows when struck by these cathode rays, making their path visible. The low-pressure environment is crucial. Too much air would interfere with the cathode rays. This diagram shows the complete cathode ray tube setup with the cathode on the left, a node in the middle, and the glowing fluorescent screen on the right where the cathode rays strike. Now let's observe how the electron beam behaves as it travels through the tube. Without any external forces, the cathode rays travel in perfectly straight lines from cathode to anode. The beam creates a sharp focus spot on the fluorescent screen, proving the rays travel in straight lines. The intensity of the glow depends on the voltage applied. Higher voltage creates brighter, faster-moving rays. Here we see the electron beam traveling in a perfectly straight line through the evacuated tube, creating a bright green dot where it hits the phosphorescent screen. Thomson's brilliant insight was to apply external electric and magnetic fields to study the nature of these cathode rays. When Thomson placed charged plates above and below the beam, something remarkable happened. The cathode rays bent toward the positive plate, proving they carry negative charge. This deflection was the first direct evidence that cathode rays are streams of negatively charged particles. The electric force on the particles equals the charge times the electric field strength. This diagram shows how the electron beam curves upward when it passes between charged plates, deflecting toward the positive plate and away from the negative plate. Thomson also used magnetic fields to further investigate these mysterious rays. When a magnetic field is applied perpendicular to the beam, the cathode rays curve in a circular arc. The direction of deflection follows the right-hand rule for negative charges, confirming the rays are negatively charged particles. By measuring both electric and magnetic deflections, Thomson could calculate the charge-to-mass ratio of these particles. The magnetic force equals the charge times velocity times the magnetic field strength. Thomson calculated that E over m equals 1.76 times 10 to the 11th coulombs per kilogram. Here we see the electron beam following a curved path when magnetic field coils are energized, demonstrating the magnetic force acting on the moving charged particles. Thomson's cathode ray experiment fundamentally changed our understanding of matter and atomic structure. Thomson proved that cathode rays are streams of identical, negatively charged particles, which he called electrons. These particles were nearly 2,000 times lighter than the lightest known atom, hydrogen. This discovery shattered the belief that atoms were indivisible and launched the era of subatomic physics. Thomson's work earned him the Nobel Prize in Physics in 1906 and laid the foundation for modern electronics. This timeline shows how Thomson's discovery of the electron led to countless technological advances, from television and computers to modern electronics that power our digital world. Thanks for joining this exploration of the cathode ray experiment. Like and subscribe for more physics demonstrations that changed our world.